Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Hello students, welcome back again into this TV learning program. My name is Jean-Marie, and today physics, as you know that I'm your teacher of physics, is for all of the senior 4. And we are still on unit number 4, work, energy, and power. But now today, lesson is elastic two-dimension corrosion. So this is what we have here. And as you remember, the last time, into the last lesson, we were discussing on this elastic one-dimension corrosion. So it means that it is a corrosion into one dimension. But today, it is in 2 dimensions. Now, students, I want you to be able to discuss 2-dimensional corrosions as an extension of 1-dimensional analysis. That is point 1. Point 2, to derive an expression for conservation of momentum along the x and the y axis. That is 2. Then 3, to describe elastic corrosions of 2 objects with equal masses. This is what I want you to be with at the end of this lesson. So get ready to be with me into this lesson. So I hope that you have the calculator and you are having the notebook to write down some explanations, okay? So let's now have a discussion. So as what we have, elastic corrosion in 2 dimensions, just it obeys the same rules as corrosion in one dimension. So I'm going, after this point, I'm going now to show you a diagram, and that diagram, it shows why we are having this 2-dimension, or what we mean by 2-dimension. But if you remember, the rules that we have defined into the 1-dimensional corrosion, so you remember, we have said that there is a conservation of linear momentum. Do you remember that? That's good. It means that we have said that during the elastic corrosion, so there is a conservation of momentum. Momentum that we are saying is, that is before and after. So we have the same momentum, right? So, and then another point number 2 is whereby we have said there is no loss of kinetic energy into this elastic corrosion. So, but as an approximation, we have said that it is better to assume that a corrosion is a perfectly elastic. That is a perfectly inelastic, because what we have, the elastic corrosion is an ideal corrosion. Do you remember? It is an ideal, which means that it cannot exist, as there is always a loss of energy in any form, whether there is a sound production in the form of heat. This is a loss of energy that we have during the corrosion, and this makes the conservation of energy that we are saying as the kinetic energy not to be obeyed. But in order now to simplify the solving of problems, we say it is a perfectly inelastic corrosion, okay? So then we have the total kinetic energy is the same before and after elastic corrosion. So note that the kinetic energy is not calculated for each direction separately, but depends on the magnitude of the total velocity of each object, each mass that you have into the corrosion. Now, students, I want you to observe the diagram. So the elastic two-dimension corrosion, so this diagram is going out to show you that we have a before we have the collision, okay? So we have a mass, that is a mass M1 with a speed V1, okay? We have M2 and it has a speed U2. That is initial velocity, initial because this is before collision, okay? What we have next is that there will be a line that is joining the two. As you see this line, it is not going straight into the center of another bore number 2. Okay? So this will now make the collision here, this bore 1, when it comes, it is striking this bore number 2, not at the center, and it makes this bore not to follow the line that we see, the dotted line there. And this will be a 2-dimension collision. It could be a 1-dimension collision if the line here was also passing through the center of the secondary bore. Okay? I hope this is clear. Because if we arrange the bores in a way that we have them on the same line means the line passes through the center of one, it is passing into another center of another second one, the same line. But these two here, they are not at the same line. And what we have there, it is the point of impact. So point where we have the interaction is going out to take place. And then, students, what is there? It is that bore 2 is being struck by or is being hit by the bore that you have there, number 13. And then here's what is going out to occur. Then the bore, there it takes this direction. Do you see that? So, and then after, when taking that direction, you see the line that we have. It is a line, of course, that would be followed by the bore here. So, but to took this direction, and it is at an angle, just at an angle theta 1 from this direction that would be followed by the bore if the line if the line passed through the center of the two bores. But remember, this is a 2-dimensional collision. So then at bore number 2 is there. It is also at another angle with respect to the line, with respect to the original direction of the bores before collision. So then we have this diagram. Now, students, as what we came now to see, in order now to discuss this question, we have to use the coordinate system. And the coordinate system that we are using here is a coordinate, of course, of the two axes. So we have a 2 axis, and whereby one bore is following a y-x-axis, another a y-axis, a y-x-axis. So, and then we have to discuss what is going now to be the momentum along the x-axis, what will be the momentum along the y-axis. This is what we have to discuss with. But here we are saying the coordinate system being considered is sometimes called the laboratory coordinate system because many scattering experiments have a target that is stationary in the laboratory. A target that is stationary means that into the study of some particles, we assume a particle into a box that is not seen, that you can't see. And it is being hit by another particle, but the speed of these two particles, you can determine them. And you can analyze what kind of a particle that was being hit, that is inside the box. You can know what kind of this particle, the composition of the particle that was hit by another one. Remember that particle that is hitting another is having a speed that is being known. And then we are assuming this particle being hit has a speed 0, or it is stationary. Okay, so then students, this is what I'm telling you now. It is here. So we are saying that we have, okay, so this is what we have next. We have, this is the coordinate system. Now, the diagram that is in here is what we are going to analyze together and then find this coordinate, or find what is happening on x-axis and what is happening on y-axis. So as what you see, before collision, it is a mass m2, and we are assuming it to be at rest. At rest, so then from the coordinate system here, system applied on the masses, that is M1 and M2, we find the momentum along x-axis and y-axis. So, and what we are saying, we have this is the ball, this is the M1, and there is another one that is stationary. It is stationary, means that this one is going out to hit with a second ball here. And to be stationary means that its velocity, its speed is equal to 0, and we have the M2. So this one is with the velocity u1. And after collision, what we have is one ball is taking in this direction, okay? So, and another, with respect to this one, we have a θ1, and this is M1. So, and then another one is taking this direction whereby we have a θ2, and you have the ball. So that is with the speed v2, and when this ball 1 has the final velocity v1. So let's make them differ, and you could now see this is the ball 1 here, another one. So, and then this can now be shown to be this one. Okay, so this is what we have. Now, students, as what we have said, there is a conservation law of linear momentum along each of these axes that we have. Then let's discuss this along the x-axis. What do we have as the momentum? So the linear momentum. So here, what we have is this, before collision, we have M1, U1, plus M2, U2, and this should now be equal to M1. Then, students, pay attention with when you have then before here, okay? So here before, let's say that we are saying here it is before. So here before collision. Then what will it be after collision? As you see on this diagram, after collision, we have the component of the velocity along the x-axis. Do you see here? If we draw the line from this vector here, if we draw the line to the x-axis, we find the component of this velocity, but along the x-axis. If we do the same for the ball number 2 here, also we find the component along the x-axis. Okay? So it means that the two components here that we have are the ones that we are going to use to express the conservation law of momentum. In other words, this will be the momentum after collision. So let's say momentum after collision collision is given by, here we have M1, then V1, let's say X. You have to understand why I'm saying Vx. The reason why that I'm saying Vx is from the component that I've told you. So we have the line from here up to the point where we have joined this one. And then we say from this point up to that one, we have a component along the x-axis. You remember that. So then this component, so you see what I'm saying here, it is the line here that is drawn, it is going to give us the component, we're calling it as V1x. Then here plus M2 V2x. This is what we have. Okay? Then from this V1x will now be equal to this is the velocity, V1, then cosine theta 1, because that is the angle that we have here. And then we have this is the hypotenuse, and then we have this as the adjacent side, and then we find this is V1 cosine theta 1. And V2x will be equal to V2 cosine theta 2, and this is the component. From here, this is the component V1, right? And then let's extend that. And then another one here, it is going to be a component that we are saying to be V1, this is V2x along the x-axis. And then students, that's what we came now to do here. So we can find, then, here we have M1, U1 will be equal to M. This is going to be M, M1 V1 cosine theta 1 plus M2 V2 cosine theta 2. This is the conservation of linear momentum along the x-axis. Okay? And I did not consider M1, M2 plus, times U1, U2, because since what we have here, we have since U2 equals to 0. Remember, this one is at rest. That is giving us here not to consider M2 times U2. U2 is 0, and you times that M1, M2, you obtain 0. We do the same thing when we have along the y-axis. What are we going to find, the students? Then you think about that one, and then you tell. So what do you think? How that what I'm going to tell you is going now to be the same as what you think about. Then, students, as you are just thinking about that, along this y-axis, we are going now to consider the y that we have here, because here we were considering x to be there. Look at the diagram, and it is the same as what we have here. So this is the component, and another component is down there, right? And then, students, let's along the y before collision. So here is what we have. The momentum is given by, this is M1, U1. It would now be equal to 1y plus M2, U2y. Now let me tell you, students. Did you see that the momentum along the y-axis before collision is 0? Do you see that? That's good, because this bore 1 is following only the x-axis, and it is not following the y-axis. In other words, if it was said now to be bouncing back, just bouncing or moving up and down, and then we could find this component along the y-axis. But now it is moving on a straight line. That's why we have the component here, even this one is 0 and this one is 0. We don't have this velocity along the y-axis. Then that is 0. But then after collision, so here's what we have. We have, in general, what we have is after and before collision. So this is what we have. We have that 0 equals to just that is mass m1 v1, then sine theta 1 plus m2 v2 sine theta 2. I'm telling you, when we use this positive here, you don't mind. This theta can be calculated to be negative. In the case, can be calculated to be negative when this theta here, well, here when we have considered to be positive. So then the theta here will be negative to mean that is below the line, below that line that is joining the center. The center here before we have the line, and it was following this line, and then the angle that is below here, it is negative, and the one that is here, it is positive. So into the calculation, this is what we obtain, okay? So then here we have before and after collision. So what we have as the conservation of momentum along the y-axis is going to be m1 v1 sine theta 1. Sine theta 1 here, because this will be considered here. It will be considered as the adjacent, as the opposite side here to this angle, and then we use this opposite side, or you can even say this is theta 1 here. So, but it is opposite side to the angle that we are having, and then we have this v1 sine theta 1. The first and the second here we have v2 sine theta 2. And then students, we can now just continue. This is explaining what what we came now to discuss there. The questions of conservation of momentum along the x and the y-axis are very useful in analyzing two-dimensional collisions of a particle where one is originally stationary. So one, we considered it to be stationary. Another, we considered it to be moving. Okay, so here we have an example. So let's consider this diagram, okay? Consider the figure below to calculate the speed of white ball if they have the same masses. I hope that you are just reading that. So can you think about how we can find that? Students, you have some second now to think about the way the question there can be solved. Okay, very good. It means that as what you see there, answer or just correction. Let's correct this. Correction of this. So as what you see, we have the white mass of the white bar is equal to mass of the black. So this is it. They are all equal. So in other words, what we have here is mass. If we say before, conservation of momentum before and after is going to be, here we have m along the x-axis. What do you think is going out to be this one? Along the x-axis we have, this is m1 times u1, then equals to m1 v1 cosine theta plus M2 V2 cosine theta. This is theta 1 and theta 2 here. This is what we have. And because we have the same mass, as we are saying, the same mass, this, let's say, the same mass, M1 equal M2, or we are saying this is M white equals to M of the black ball. And then, students, we can substitute to find this one. Here we have, then this is U1 equals to V1 cosine theta 1 plus V2 cosine theta 2. And what is going to be the one along the y-axis? What do you think is going to be that? As what we have said, in a simple way, we can now use this one. And then we find this is 0, then equals to V1, then sine theta 1 plus V2 sine theta 2. And then, students, can we substitute? If we substitute, then what we have from this equation down here, we have the problem, we have a 4, which is equals to, this here it is 2, this is 2 cosine 45, then plus this is not known, plus V of the white, okay, cosine theta of that white. So, and what is next to you is 0 here equals to 2 sine 45 plus, this is 45 plus V of the white sine theta of that white ball. We have the two equations that we can use to find the theta. So there it means that we have V white cosine theta white equals to 4 minus 2 square root 2 over 2. And this one also, it is V white sine of the white here equals to, you see, equals to minus 2 square root 2 over 2, because it is this one that comes to this other side, okay? Then, students, if we divide this equation to this one also, we find tan theta, which is equal to minus square root of 2 over, so over 4 minus square root of 2. What is going out to be this value? The value there that you calculate can give you theta, which is equal to the angle. So I want you now to make it as an activity. Do it as your work, and then you finish the work, but you can also find the speed. And I see you by the next time correcting this or finishing this question with all of you. And thank you very much for having me today. We meet again by the next time, but trying to correct the question that you have in front of you, but follow this one starting by there, and you find that theta. Be good. Bye-bye.